I'm recording. This is 18.21, convex and concave lenses. There are two different main types of lenses. We have the converging lens, which is what you can see on the left, where all the light rays converge into one. This is like your magnifying glass. When you go outside, it takes all of this light from the lens and breaks it all, or pushes it all the way down, bends it, so that it all is one focal point. And that's where you would put your ant that you want to, catch on fire. All right, the one on the right is a diverging lens, and as it sounds, it's diverging, so the light rays are not going to converge in one point, which means you're actually going to end up with a virtual image. So if you were on this side, you could look in and see a virtual image over here. Virtual images are a little strange because, again, they're not real. We can see them with mirrors because they're inside the mirror. But with the lens, you're like, okay, wait, how am I going to see that? Well, it's the same thing. It's inside the lens. You have to look into the lens, and it looks almost like a hologram. Like it's not really there. Like when you look through the lens, it looks like the image is right here, but when you look away from the lens, there's nothing. So it's inside the lens. You can do this if you wear glasses, bring them in front of you like this, so they're further away, and everything that's going through the lens actually looks like it moves. That's a virtual image. So these are the two main types of lenses that we're going to use. There's lots of other types of lenses, and I'll kind of show you what some of those are, but we're going to deal with these two in particular. If you look through a nice flat plane of glass, like our window here, it's not warped or anything. So pretty much what's outside is what we see. There's no bent line or anything like that, so it doesn't change. But when we look through a lens, let's figure out which one's which. This one is a converging? Okay. This one's our converging lens. If it's really close to your eye, you see one thing, where if you move it further away, you actually see everything's upside down in the lens. So that one is the converging lens. And then we also have the diverging lens, which for me, when I look through it, I see everything's fairly crisp and clear when I look through it, no matter where it's at. When we look through a lens, the lens itself warps the light rays. So we actually see a warped view of the world. And you'll see weird images. So you can see really big images, really small images, crisper images, blurry images, upside down images. The lens on our projector takes what's projected through it and makes it larger so that we can see it up here. We're only going to be dealing with spherical, thin lenses. There's lots and lots of different types of lenses. We're just going to deal with these two thin spherical lens types. So our converging lens, it takes parallel light and bends it into a single point. And our diverging lens takes parallel lines and bends them apart. So you actually end up with a virtual image on the other side of the lens. Or I guess on the same side that the light's coming from. There is lots and lots of different types of lenses. We're only going to talk about biconvex and biconcave, but I put this up here so you can see all the different types. And depending on your eyesight, they are going to use different combinations of these to fix the problems. This one is our converging lens. It's biconvex, so it sticks out on each side. In between, we have the plano, so flat convex. We have concave convex, where this is a different curve than this. We have meniscus, where they're both the exact same curve. We have plano concave, where this one's inside and this one's flat. And then we have biconcave, where it's caved in on both sides. So this will be our diverging lens, and this is our converging lens. But we have all of these different ones in between that you could also calculate, but we won't do it in here because it gets a little bit more complicated. But you don't need to write them all down, just showing you. All right, again, so we're using the converging and the diverging lenses. The converging lens, or the biconvex lens, the one that sticks out on both sides, has 6 possible different image locations. And I'm going to pass out this handout here that has all those locations on it. It is a lot like the concave mirror, how it depends on its location, whether you see something that's inverted or real, virtual and upright, or inverted and real. For the converging lens, the focal length is positive, which is also why it's very similar to the concave mirror. Now the diverging lens, the one that is caved in on both sides, the biconcave, that one only has one type of image. This image is always virtual upright, and its focal length is also negative, just like the convex mirror. So it doesn't matter where you're at, you're always going to end up seeing a virtual image. Now you're seeing this stuff up here. This is FI and FO. I'm going to talk about that. Instead of one focal length, we actually have 2. And that's because it's biconvex. So we have one curve here and one curve here. So you're going to have a center and a focal length on both sides. This 2FO, you do not include in your ray diagrams. You're not going to use it. You're not going to calculate it. It's not even there. It's just because when it's at 2FO, it ends up at 2FI on the other side. So that's why it's in this particular one. The focal length will be FO and FI on both sides of the lens. They are the same length. So if I draw a quick little sketch of that, this is what you're going to start out with on your paper when you write one of these. You have a concave lens, and I'll write a little converging lens. Still got to get off of here. Converging lens, and then our focal point, one on each side. This will be FO and this will be FI. This is for our converging lens. Now the reason that we have FO and FI is because if you took this and you extend it into a giant circle, you're going to end up with C, and then FO halfway between, which that's not halfway, but pretend it is. And then on this side, you have a big circle, and you're going to have the center point. And then, these are bothering me. Halfway between, you'll have your focal point here. So since you have 2 edges, you're going to have 2 focal points. Now for your ray diagrams, you don't need to worry about C. You're not going to have a radius of curvature. You're just going to have a focal point. And it'll say the focal point. So that's what you're going to start with. And then your object. And we'll put our object on the left. One other thing that's a little bit different is because light rays go through the lens, this side, the right side, Q is positive now instead of negative. So that's our only changes. Instead of F and C, we have FO and FI. And instead of this being Q negative, it is now Q positive. Now this focal point is positive for converging lenses. let's look at diverging lenses real quick. I want you to pay attention right here. I want you to look at this dot. For diverging lenses, FO and FI switch. So now this is FI and that is FO. So let's draw a little setup for a diverging lens. For a diverging lens, F and F, except for diverging, FI, FO, negative focal length. All right, the equations are the exact same equations that you use for mirrors. Same equations. 1 over F equals 1 over P plus 1 over Q, and magnification is pi over ho, and it is also equal to negative Q over P. Same stuff, nothing new. So if you didn't learn the equations for mirrors, guess what? You got to learn them from lenses too. And I do have your test graded. It took me 4.5 hours yesterday. I do not hand them back, but if you'd like to come and look at them, you are welcome to do that. And they should show up on your deadline tonight after 4. All right. So let's see how to draw the ray diagrams for these. You can follow along on that handout that I gave you. I'm going to go through each one of them. This one you're never going to see. I'm not going to make you draw it. This one is parallel. So this would be like the sun. This is how magnifying glass works. The object is infinitely far away. And it follows the same sort of rules. Let me write those rules down real quick. The rules are still parallel and then through F, through C, and then F through parallel, except for we do FI and FO. That is the only difference. So here is parallel and through FI, and then through the center, and then parallel and through, well, this one doesn't work. All right, this one's infinitely at the sun. Don't draw this one. Don't draw any of them, actually. We're just going to walk through them. All right, here's an actual one. This one, when it's further than 2 equals FO, so further than C, is parallel and through FI. And then from the top of the object, we're going to go through C. Now, there's no C on here, so our C is the center of the lens where it meets the axis. Okay. So top of the object with C. And then we go through FO and parallel. So you end up with an image on the other side. It's inverted and it's real. I'm going to run through all of these and then we're going to do some practices. So don't freak out. I'm not expecting you to draw these. All right, next one. Parallel through FI, through the center, through FO, and then parallel. Real inverted. You guys remember what happened when we moved the object to FO in the mirrors? What was right on the focal point? What kind of image was produced when it was right at the focal point? It was that weird one, the last one on your test. The lines were parallel, so you didn't get an image. The image was at infinity. Well, the same thing happens here when it's F, like when it's at F on the converging lens, parallel through FI, through C are perfectly parallel, so they never converge. And that's because FO is right below it, so it's never going to hit the lens. It's never going to produce that image. So that's the weird one. All right, and then when it's super close to the lens, it does this weird thing. It goes parallel through FI, through C. Most of the time we're expecting an image on this side, but this time it bounces back. So that's a little bit tricky. Watch out for that one. And then the last one that messes people up is through FO, which is behind it now. And that's fine. Just go until you hit the lens and then parallel, and you end up with a large virtual image behind it. All right, this last one is a diverging lens. It follows the same rules, except for FO and FI are switched. So when you go parallel through FI, you have to come back. And then through C. And the last one, which people get confused, is go from the top of the object through FO, but you hit the lens. So when you hit the lens, you have to bounce parallel. So you never make it to FO. So that's the hard one. And you end up with a tiny little virtual image right in front. Yes?
For that one, why is the dotted line on this side?
For all of them, oh, that one's messed up. That one should be dotted on this side.
Oh.
Yeah. For lenses, the real side is the right side, so those should all be solid. And for the left side, those should all be dotted. So this one's supposed to be dotted, and that one's supposed to be solid. That one's just messy. I'll fix it later. All right. The last little thing we're going to cover before I do a practice with you is chromatic aberration. The thicker the lens, the more curved the lens, the more it's going to refract like a prism, where it breaks these wavelengths up because they're all different colors of different wavelengths. It ends up spreading them apart. So when you have lenses, especially really curved lenses, you're going to get this rainbow effect. If you imagine looking through binoculars, you get that rainbow effect. And that's because all the different wavelengths are actually converging in different areas. So when you focus it, you want to try to focus it somewhere in the middle, where some of the blue is focused and some of the red is focused. Otherwise, if you just focus it at the red, all the blue is going to look all blurry and it'll look weird. So it's hard to get rid of this, but that's why they put other little flat, thick lenses on it to try to fix that. But that's called chromatic aberration, and that's the rainbow effect due to the refraction of light through a lens. This table's in your book. You don't need to write it down. It's just in your book. If you are kind of interested, you can take a look at it. It might help you with the placements. Your handout that I gave you will help you with that too. All right, so let's do a practice. I especially want to get one in before the BCC students leave. So here we go. It says the focal length for a converging lens. One sec. Let me clear this. The focal length for a converging lens is 3 centimeters. What's the image location and height if a 1 centimeter object is placed 4 centimeters in front of the lens? So just like you're set up for mirrors, we're going to do a lens one. So take your ruler, put it across the width of your page. Let's see if this works. A little crooked. That's okay. About 2 or 3 lines above and below. We have a focal length of 3 centimeters, an image height of 1 centimeter, and an image location of 4 centimeters. Do you like my magic, by the way?
Yes. Yeah.
You guys all freaking out because magnets? All right. So we got our principal axis and our lens axis. It's coming out good. Now, what I'm seeing, and I'm seeing this less and less, which is really nice, but some people, when they draw the mirror curved over top of it, are using that curved part to bounce off of instead of the flat part, and we want the flat part. So if you struggle with that, you can just write a little converging lens symbol up here instead. But how you'll see it in all my drawings is a converging lens that looks like this. It's just that people tend to, when they do the bending part, they won't go to the axis, they'll go to the edge. And we don't want that. So just use the flat part. Now it's converging, so the focal point is positive F. Now we want to put in our focal length. It's going to be 3 centimeters, so make sure it's 3 centimeters on each side. And our object is at 4 centimeters in front of the lens. So we have P, we have F, we have F. You guys are talking too much. Don't like it. And for those of you that need to make sure you're putting in the right spot, you don't need to draw these. This is just for you to use when you're looking at my diagram. Now, this is a converging lens, so FO is over here and FI is over there. And this is 1 centimeter tall. Questions on the setup? No? Okay, we're all good? All right, we're going to do the rules. Parallel, and then through FI. So from the top of the object, we're going to go parallel. And then where we've hit the lens axis, line that up with FI. And on the right side this time, this is solid, and this part is dotted. If you don't like making the dotted lines, that's okay. You can make them solid. It's not that big a deal. It just indicates that this is the virtual side and this is the real side. Next one through C. Now remember, we don't actually have a point C, we have the center. So we're going to line up the top of the object with this axis part here. So top of the object, the axis, and as you can see, my lines don't converge yet, so I need to keep drawing until they do. All right, last one is FO and then parallel. So line up the top of the object with FO. Oh, this is huge.
This one.
Yeah.
FO is where the object is and FI is the focal length.
They're both the focal length. We have two focal lengths because we have two edges. With the mirror, you know how you only have one curve, so the focal length is here. With the lens, you have two edges, so you have one here and one here, which is why there's two. Now, they're the same length for this particular lens that we're going to be doing for all of our lenses. When you says focal point, you put a focal point on both sides. And then we just label with converging, the left is O, the right is I, diverging their flip.
Okay, so diverging it would be FI on the left side and FO on the right.
Yes. All right, this one is not working out for me. I might have done something wrong. Let me check my measurements. This is really far off. 1, 2, 3, 4. 1, 2, 3. Yeah, it seems right. All right, let's draw it. It's kind of off, but sometimes that just happens. As you can see that my lens axis is not long enough, so I just need to extend it a little bit. There we go. And then parallel. And it's so hard for me to tell what's parallel from this close-up. As you can tell, I am not having such a good time with this converging point. It's a little off. So that means my answer is probably going to be a little bit off. It is.
I think your red line isn't parallel to the axis.
I think you're right. It definitely seems wrong. Okay, I'll try to redraw it and see if I can get it to go better. All right, and let's look at this red one. It's not very good. Try to fix it. Does that look better?
I would go right side down a little bit.
Right side down. You sure? Like that? That looks better?
Yeah.
All right. Again, it's kind of hard to tell from this close up. Better?
Yes.
Okay. Let's try it that way then. All right, it's getting better. Getting closer to where it's supposed to be. All right, my converging point could have been a little better, but it'll work for now. It's doing weird things on the program, but that's okay. All right, our image will be at this weird little, you see this triangle sector here? That's what happens when you make a couple of mistakes in your ray diagrams. It's okay. You can leave it. It's fine. It's small enough. It's all right. Just kind of pick somewhere in the middle of this triangle. Draw it to your principal axis. And this is your image Q. and make sure you find HI. So we're going to measure these things, which is going to be huge. Mine's 10, almost 12 centimeters. Now it's on the right side, which normally for mirrors would make it negative, but it's actually positive for lenses. And then our HI, our height, is negative 3 centimeters. And it's negative because it's inverted. So you want to write down inverted. A lot of people weren't writing down on their tests, they weren't saying inverted and real, so they lost 2 points because that was part of the question. So make sure you say inverted and real. If it's inverted, it's real. If it's upright, it's virtual. You're never going to have a real upright answer. It's not going to happen. It will never happen. So I think maybe only 1 or 2 of those. Don't guess here. If it's inverted, if it's upside down, it's inverted, and if it's inverted, then it's real.
In all cases, or just for the...
All cases. Mirrors, lenses, doesn't matter. If it's inverted, then it's real. All right, now let's do the math for this stuff. We've got 1 over f equals 1 over p plus 1 over q. It's a converging lens, so our f is positive. So 1 over 3 equals 1 over 4 plus 1 over q. So 1 over 3 minus 1 over 4 gives me 1 over q. And I only saw this on a couple people on their tests, but they were not solving for q. They just leave it like this. I can't give you full credit for that. You've got to answer it all the way, flip-flop the bottom and the top. Q is equal to 12. Oh, look at that. Not bad. Not bad for a terrible ray diagram. And the one other thing that I saw a lot of people doing, they left off their units. You lost a point for that. Make sure you put the units on. It's an easy point. You can get that point. Centimeters. All right, the next thing that you want to do is magnification. Magnification is equal to negative q over p. So negative q, you want to use your calculated value, not your measured value, because you're double checking to see if your ray diagram is correct. So if this was a different number, if it was like 12.5, then we put the 12.5 in and not what we got from the ray diagram. Because we're trying to check it here. That's the point of doing this. So negative 12 over, and p is 4, so we got negative 3. Which makes sense because it is upside down. It's inverted, so it's going to be negative. One last little check is our magnification using the ray diagram values. So this is the given values, this is the ray diagram values. It's HI over HO, just like indoors. I hope. Okay. HI. We're going to put in our value that we measured over HO, which is given to be, that's H. Oh, there we go. 1, giving us negative 3. And these two things match as well. So it is drawn correctly. Again, they don't have to be perfect. They just have to be kind of close. Okay, I don't have enough time to do the diverging lens. But what would change here is the FO and FI would switch, and the focal point would become negative. So when you do the calculations, you just make this negative. And when you do the rules, instead of going forward through FI, you come back through FI. And when you go to FO, you act like you're going to go to FO, because it would be right here. But when you hit the lens, then you go parallel. And you'll end up with an image over here instead. And if you need to see that, it's on your handout. It's on the back page with all the words. All right, your homework is that worksheet that I handed out, 1 through 4. I want you to do the ray and diagrams and the math for 1 through 3. And then you can just show your math for the table at the bottom. You don't need to draw ray diagrams.